Good evening, everyone. My name is Ethan Hurst, and I am a junior in the Randall Research Scholars Program, double majoring in mathematics and English. And this semester, my research project was on the two-dimensional Jacobian conjecture, studying specifically the generic case. This project is joint with Dr. Kyung-Young Lee in the University of Alabama's math department. He functioned as my project director, as well as Dr. Lee at the University of Illinois at Urbana-Champaign, and George Naser at the University of Nebraska at Lincoln. So the Jacobian conjecture is one of 18 Smale's problems. One of the most fundamental theorems in calculus is the local inverse function theorem, which states that if the Jacobian of a map does not vanish at a particular point, meaning it doesn't go to zero, then we know that the inverse map exists locally. The goal of this project is we want to globalize the idea in that theorem. We consider only polynomial maps, as non-polynomial cases can't be described in a nice way. The Jacobian conjecture is as follows. So if we let K be a characteristic field, or a field of characteristic 0, we let n be a positive integer, then we want to consider a polynomial map, and we can think of this as a vector-valued function mapping functions in an n number of variables to functions in an n number of variables, which is given by the following decomposition with that pi function. Then if we define the Jacobian of the map as usual with the following partial derivatives, if that's a non-zero constant, then we know that the map is bijective, which means specifically that we can find an inverse of that vector-valued function. So for this particular project, we focused only on the two-dimensional case, as that allows us to simplify the computational complexity of the conjecture greatly. It's well known that the following conjecture, which I'll show in a minute, is equivalent to the two-dimensional Jacobian conjecture, but we first need to define the notion of the Newton polygon. So Newton polygons are described as follows. If we have any sort of polynomial, which we give as a degree decomposition given here in a polynomial field in K, we describe the Newton polygon as the convex polygon containing those points, and how we can think of that is we take the degrees of the variables in each term and we map that in the Cartesian plane. And so this allows us to give an equivalent Jacobian conjecture statement using the idea of Newton polygons. So if we let K again be a field of characteristics 0, and we suppose that f and g are polynomials in this polynomial field K, we want f and g to satisfy the following. We want their determinant, or the Jacobian, given by these square brackets, to be a constant within the field, which means the Jacobian doesn't contain any variables. And we also want the Newton polygons of f and g to not have any edges that have slope 0. Then what the Jacobian conjecture says is that the Jacobian of these two functions is equal to 0, not just a constant. Abiyankar's reduction theorem, and Abiyankar is a mathematician that popularized the Jacobian conjecture. He came up with this theorem that allows us to greatly simplify the Jacobian conjecture itself. So if we let f again be a Jacobian polynomial, we assume that the Newton polygon has no negative edges. Then there exists this function called phi, which is an automorphism from the polynomial map over K, such that we can reduce the degree of f using that function phi. So phi is an automorphism, which means it's taking an algebraic structure and allowing us to simplify it, because the systems are considered equivalent under the automorphism. So this allows us to greatly reduce the complexity of the problems we are looking at in the two-dimensional case. Then from here we can define the notion of directionality. So again, we assume that the Newton polygon has no negative slopes. And then, so an element in this polynomial map, we can say it's pointed at a point in the integer plane if the coefficient of the term is equal to 1 in the Newton polygon. And then we say that the Newton polygon is contained in the quadrilateral that is defined by that point. So you take the point with the axes, create a quadrilateral, and the Newton polygon should be contained in that point. So this is, you can think of this as the biggest point on the Newton polygon that is the furthest away from the origin. So the goal of our project right now is to simplify a seemingly very complicated formula, which is known as the Magnus's formula, and apply the results of that formula to this specific case. The formula has been known for about 60 years, but hasn't shown up much in the research afterwards and hasn't received much attention. So this is Magnus's formula. So if we consider any homogeneous degree decomposition of f and g, and we write f as these degree decompositions, then we let d and e denote the maximum degrees of f and g respectively. Then we have this enormous formula, which I will not read off to you all. The sum without the limits is extended over all combinations of non-negative integral exponents. Satisfying in that bottom equation is a system of linear equations in nu. So a quick note on computation, we use SAGE math, and SAGE stands for a System for Algebraic and Geometric Experimentation, which has allowed us to greatly simplify this enormous formula and use it in this specific case. SAGE is a computer algebra system which is coded in Python and is able to manipulate very large algebraic expressions. SAGE math has allowed us a lot of flexibility with our capabilities to experiment with these very large two-dimensional polynomials, as well as consider divisibility factors that allow us to reduce the Jacobian in this specific case. From here, we can define the notion of generic pairs of functions, which is a bit more technical. We say that a pair of functions, f and g, is generic if, and there are three conditions here, so if the Newton polygon is pointed at a sub 1, comma a sub 2, so that direction of the biggest point on the Newton polygon, if the Jacobian is in the field and is a constant, and this expression here, we can think of this as a Newton line that's radiating out from the origin. So we essentially are creating a polynomial from this Newton line, and this is where the generic definition really holds its weight. It's not divisible by the square of any polynomial, which has at least two terms for each of the line segment radiating out from the origin through the specific point of directionality. And then the following theorem gives our main result so far. So we restrict f and g to be generic functions. We fix a at 2, and that comes from that formula d over the greatest common divisor of d and e, and recall d and e are the maximum degrees of f and g. And we let b equal e over that greatest common divisor. Then our equivalent Jacobian conjecture also holds true. And more precisely, we've actually been able to come up with explicit formulas for f and g that allow us to break this down and compute it more effectively. And that capital P bar is also a polynomial in the polynomial field K, and those coefficients also reside in the field K. So, and in particular, this also implies that the Jacobian is 0, which is exactly what we want for the Jacobian conjecture. That represents our work so far. Future directions, we are still studying the two-dimensional case. Ideally, we want to create a simplified version of this and get something more general where we aren't fixing a equal to 2. Ultimately, moving forward, we want to generalize to higher dimensions and also find a general and easily comprehensible statement that holds true regardless of the degrees and dimensions of those functions. And with that, I'll field any questions.
If you solve the Jacobian conjecture, what are some applications of that solution?
Right, so the Jacobian conjecture is a big problem in algebraic geometry, and it has applications in any field that is related to algebraic geometry. So any sort of linearization or cancellation problems. Quantum field theory is another field that comes to mind, and any sort of problem that involves modeling with polynomials, especially if we can find some closed form for the inverse of that mapping, that will prove extremely useful for modeling problems as well.
So with the Jacobian conjecture, how difficult is it to solve? And do you have an estimate of like how long people have been working on this and how long they've been trying to solve it?
Right, of course. So The Jacobian conjecture is notoriously difficult. There are many published incorrect proofs of the Jacobian conjecture, and the fact that it's categorized as one of 18 Smales problems, Stephen Smales was a famous mathematician who published these problems. It's a very hard problem. It's been worked on for over 100 years, and a lot of its notoriety comes from many of those subtly incorrect proofs.
What are some of the methodologies used with the Sage Math software?
Right, so what we do is we create general functions, F and G, in the Sage Math software. And it looks a lot like Wolfram Alpha, so we can create general functions, and then a lot of what Sage is capable of doing is it can take these functions and manipulate them with a high degree of efficiency. So it can manually compute the Jacobian even for functions with a large number of terms. I've seen it capable of handling things with hundreds, thousands of terms in them. And then what we can do is we can go through and using divisibility conditions on the Jacobian, we can rule out terms in the Jacobian that have variables in them, because ideally we want to reduce the Jacobian to some constant or zero. So we can use Sage Math to look at divisibility conditions and reduce the Jacobian that way.
Great. Thank you, Ethan.
Thank you.